Hello everyone, my name is Muhammad Al-Hanahna. Today I will be presenting our paper, Scalable Analysis of Interaction Threats in IoT Systems. This is a joint work with my colleague Clay Stevens and my advisor Dr. Hamid Bagari. The number of IoT devices is growing, therefore it is expected by 2025 the number of connected IoT devices will be increased by 145%. However, this increment in the number of IT devices comes with safety and security issues where attacker can unlock doors, tamper with the temperature, and get access to Wi-Fi devices by exploiting vulnerable smart home devices. So this raises the question, what makes IoT apps so vulnerable? To answer this question, we need to understand the smart home environment. Therefore, let's have this scenario where we have lamp, overhead light, and light sensor. Those devices will be controlled through SmartThings IoT applications. SmartThings is a well-known platform for automating smart home activities. The first application is IFTTT, if this, then that. This is a third-party cloud provider for automating IoT applications. This application will be triggered when the brightness is changed and will be switching off the overhead light. The second application is a Groovy application. It's called multi-switch. It's provided directly by SmartThings. It will be controlling the lamp and the overhead light. The third application is in the format of IFTTT as well, and it will be switching on the lamp when the overhead light is switched off. Also here the lamp and the overhead light, when they are switched off, this will be affecting the light sensor. As you can see, we have physical and cyber events that are used for the interaction between IoT apps and IoT devices. To understand the interaction in this smart home environment, let me explain the architecture of IoT, where we have cyber space that has several cloud provider. Each cloud provider provides IoT applications. Each IoT application consists of behavioral rules, and each rule is formalized as triggers, conditions, and actions. Those actions will be sent out to the physical environment where we have actuators and sensors. The actions will be sending commands to the actuators. The actuator will be executing those commands. This will be affecting the IoT environment and generating new events that will be triggering new behavioral rules. If we apply this concept into our example here, we can see the IFTTT application at the top will be triggered when the brightness is changed. Then it will be sending switch off command to the overhead light. At the same time, the switch off command will be sent to the multi-switch because it's also controlling the overhead light. Then it will be sending two switch off commands to the overhead light and the lamp. This also will be changing the brightness and will be affecting the light sensor. At the same time, this will be triggering the IFTTT rule because the overhead light is switched off, and therefore it will be switching on the lamp. According to this scenario, we can observe several issues. The first issue here is the interaction between the IFTTT application at the top and the multi-switch Groovy application. We can see there is an infinite loop of interaction between those applications, where switch off command will be sent repetitively to the overhead light and the lamp. The second issue here is the interaction between the Groovy application and the multi-switch and the IFTTT rule at the bottom, where conflicting commands will be sent to the lamp. Safety and security has been studied in the state of the art from different angles and different perspectives. In general, we identify three major limitations in prior work. They are constrained in terms of either considering physical space or cyberspace, but they don't consider both. The initial configurations of the IoT applications are manually identified. There are compatibility issues by considering or focusing on certain IoT platforms without performing cross-platform analysis. Therefore, some unsafe interactions will not be detected. Therefore, we need to have a scalable approach where we consider interaction of in the cyberspace and physical space, exploring all configuration space, and performing cross-platform analysis. Therefore, our insight to perform compositional and scalable analysis to detect interactions between IoT applications. The first step we performed, we identified the interaction threats, all potential interaction threats that will be leading to threats due to the interaction between IoT devices. We identified two major interaction threats: direct interactions and chain of interactions. And under each category, we identified a subset of interaction threats. So in total, we identified 5 types of interaction threats. We formalized those interaction threats in our paper. You can find the details. But here for the presentation, I'll be focusing on the interaction threats that I'll be showing you here based on our illustrative example. The first interaction threat, we call it action repeat, where the interaction between the IFTTT application and the Groovy application will be sending switch off command to the overhead light continuously. And the second interaction threat is called action, where conflicting actions will be sent to the lamp. After identifying those interaction threats, we propose our IoT-COM approach that can detect all types of interaction threats. IoT-COM expects as input a set of IoT applications, and it tries to identify all potential unsafe interaction between those applications. IoT-COM consists of 2 components. The first component is behavioral rule extractor, where we perform static analysis for each application independently and individually. Then we formalize those applications and provide them to our formal analyzer, where we perform bounded model checking. Therefore, through the combination of static analysis and the lightweight formal analysis, we can provide the scalability and the compositional analysis. Now I'll be focusing on the first component, the behavioral rule extractor. We perform 3 main steps: building ICFG, converting to BRG, and generating rule models. For building ICFG stands for Interprocedural Control Flow Graph. We perform static analysis over the AST graph. Then we generate CFGs for each method in the IoT application. Then we connect those CFGs together by constructing the call graph to have this ICFG. Now let's have this, to illustrate this idea, let's have this example. We have from the multi-switch application. The subscribe statement here represent a trigger of this application, which will be invoking the lights off method. Then we generate the CFG of this method lights off. After generating the CFG of this method, we perform the same steps for the other methods in each application. And then we connect those CFGs together by relying on the call graph to generate the ICFG. After generating the ICFG, we convert this ICFG into BRG. Basically here we're identifying the APIs that is related to our analysis and will be affecting the IoT environment. And here we are relying on SmartThings documentation for identifying this set of APIs. As an example here, let's for the lights off, this is the CFG. We iterate each node and to generate the BRG nodes of each node in the ICFG. Here, then we iterate each statement. For example, the timestamp will not be used, therefore we discard it. The second statement is a conditional statement, therefore we convert it into conditional node, conditional BRG node, and then we converted it into 3 tuples: device, attribute, and value. Those tuples are required by our formal analyzer, as I will describe later on. Then we do the same steps with each node and we annotate each node based on its type. For the false branch here, it does not contain anything that will be affecting the environment. Therefore, we discard this branch. Then we perform the same step for the second method here for this CFG of turn off lights. We generate the corresponding BRG nodes. Then by the end, we will have this graph where the BRG graph where we have identified set of triggers, conditions, and actions based on the IoT architecture that I described previously. For trigger, we already extracted it from the subscribe statement. If you recall in the code snippet, we have here 3 conditions in this rule, and we have here one action. Then we convert those triggers, conditions, and actions into the formal specifications that are required by our formal analyzer. For the formal analyzer, we provide the formal specification for our IoT applications. We also provide for the formal specification of smart home model and the safety and security properties that we want to verify. So our formal analyzer, we used Alloy. It performs lightweight formal analysis by automating the analysis of converting the predicates into SAT solvers. Then it verifies whether the properties are holding or not. Here I will be explaining the main specification of our smart home formal model. We have first component a set of IoT devices. Each device consists of several attributes. The attributes maintain different values. And the second component here, we have set of IoT apps. Each app consists of set of rules, and we formalize the rules as trigger, condition, and actions, which is the IoT architectures that I described earlier. And we formalize the triggers and conditions and actions based on the 3 tuples that I mentioned in the BRG graph. Basically, those tuples are reflecting the devices that will be performing the activities. Now the third component, which is the physical environment, where we have uh, connection between sensors and actuators over certain physical channels. And for identifying those channels and the corresponding actuators and sensors, we relied on heuristic analysis based on prior work to identify those information. Now for the IoT, the specification of the IoT applications, as you can see here, we generate the specifications individually and independently of each other. Therefore, we can fulfill the requirement to perform compositional analysis. Here I'll be showing the first assertion that we used for verifying whether we have action, repeat. And here is the second assertion that we used for identifying action, conflict. We provide all this information to our Alloy analyzer. Alloy will be using off-the-shelf SAT solver to verify the safety properties are holding or not. And based on that, it can generate counter examples. Alloy here is a lightweight tool to perform bounded model checking. Therefore, we can achieve scalability. Then by the end, for our illustrative example, Alloy can identify the 2 violations that we have, the action, repeat, and the action, conflict. For evaluating our approach, we perform several experiments. In the first experiment, we compared the accuracy of IoT COM in comparison with Soteria and IoT SAN. We used publicly available benchmark applications, and we also developed 3 benchmark applications that are also available on the website of our project. Those 3 applications involves interactions by threats over physical events. The purpose of this to verify the capability of our tool in comparison with the other tools. We computed the accuracy based on the test cases that we have. We can see IoT COM can outperforms IoT SAN and Soteria. Basically, IoT SAN and Soteria are missing cases because they don't have the capability to detect interactions over physical space. For evaluating the performance of IoT com with real-world applications, we use two datasets consist of Groovy and IoT and IFTTT applications. We divided them into 622 non-overlapping bundles. Each bundle consists of 6 applications, and we used 36 safety properties. In total, we detected about 2,900 violations. This is the distribution of those violations. The majority are from action trigger with the percentage 35. And in second place, we have action with our repeated or conflicting actions. In the third experiment, we analyzed the performance of IoT com in terms of required verification time in comparison with IoT SAN. We used 11 bundles of real-world applications. On average, IoT com outperforms IoT SAN by 92% without sacrificing detection capability. Finally, this work can be extended by considering contextual information like number of rooms and different floors. In the smart home model, synthesis can be considered for automatically generating safety and security properties. Enforcement can be applied to prevent unsafe interactions. In summary, in this work, we are addressing the safety and security concerns that are resulted by the interaction between IoT applications and devices. First, we identified the interaction threats between IoT applications and devices, and then we propose IoT com for addressing and capturing those interaction threats. Finally, we show the capability of IoT com, and we evaluated IoT com from different perspectives, and we show how it can outperforms existing techniques. Finally, thanks for listening, and I would be happy to answer your questions.